Okay, this is lesson 13.3.1, how are velocity and position related? So there's several ways to understand motion. One way is to graph how far an object is. This creates a position graph. Another way is to consider the rate at which an object is moving. That would be a velocity graph. So we're going to investigate both types of those in today's lesson, and we'll see some kind of similarities there. So in 96, it says you described one particular motion scenario with two different graphs. Sketch both a velocity graph and a position graph for the following scenarios. For each part, vertically align your position graph and velocity graph so that the scales align. So you can look for connections, right? So A, we're going to walk for 5 seconds. So we're going to draw a position graph. So we'll have distance, right, and time. That's our position, right? And then right below it, we're going to have velocity graph. So again, time and velocity. Okay, so it says we're going to walk for 5 seconds. We're going to stop. We're going to stop for 5 seconds. And we're going to repeat this pattern, right? So walk for 5, stop for 5, walk for 5, stop for 5, right? So you can kind of see, right, 5, 10, sorry, I'm off scale here, 15, 20, 25, 30, right? So your position graph is continually, increasing distance, right? But your velocity is just going to be 5, stopped, right? Let's do this in this so you can see it's 5, stop for 5, walking at that same rate, stopping, walking at that rate, stopping, right? So you can kind of see here these connect, right, in the sense of my velocity is this walking rate and then a stopping rate. Okay, the next one, we're going to go walk for 10. So we're going to walk for 10 seconds. We're going to stop for 15 seconds. Then we're going to run towards the finish line, right? So what happens there on our distance or our position graph, right, is that running slope, it's increasing distance at a steeper rate than this. This is a walking rate. This is a running rate, okay? And I could make those different. Like if I really needed to distinguish the difference, we could say walking rate, stop, running rate. Like so, just where it increases more, if you want to make this more vertical, where it increases more, okay, then our velocity graph, very similar, right? We'll have a walking velocity, a stopped velocity. Again, I can do this in red so you can see it, right? And then a running velocity. That velocity is going to be higher than the walking velocity. Okay. So I think you kind of get the idea there. Like your distance, you have this slope increasing, right? Velocity, you just have like a horizontal line at the velocity that you're walking or running at. There's no change in it, right? So looking at 97 here, the graph at the right's a position graph. So write a scenario, some sort of, we're walking or for 2 minutes, we rest for 2 minutes, we're walking again, right? So just having some sort of scenario, driving a car or anything like that, right? The velocity graph, again, would look similar to this one that we just did, right? It's going to look very similar to this. You're going to have a certain, velocity, a stop time, and then a little bit more increased of velocity. Okay, 98. The graph is a velocity graph. Sketch a position graph. So anytime you have a constant velocity, your position is just, it's just going up. It's just a linear, straight line function, right? It's increasing. 99, use the graph at the right to complete the following. Sketch a velocity graph. So again, this is 99, right? Velocity. So we have a constant position times increasing, so we have a constant velocity, and then we have a stopped, we're resting, right? So we have this constant slope velocity, and then we have a velocity of 0 because we're resting the rest of the time. We're not changing distance. Okay. 100, the graph the velocity with respect to time for this graph. All right, so we have a velocity of 5. So let's say this is 5. So we have a velocity of 5 for 10 seconds. We have 0 for 10 seconds. And then we have 5 for 10 seconds. Okay, what does the area under the curve represent? Okay, here's the cool thing. The area under a velocity curve. So let me explain how this works, right? And we've talked about this before. Velocity is some feet per second, right? And then area is times, right? It's base times height or length times width. So our height is feet per second. Our width is seconds. So if we multiply those together, we're left with feet, which is a distance. So what does area under the curve represent? It represents distance. What is that total area under the curve? Well, let's see. 5 times 10 is 50. Same deal here. 5 times 10 is 50. So we have 100 feet is our actual area under the curve there. So that's kind of cool. And then it says sketch the position graph. So that position graph, we would go up to 50 in the first 10 seconds. We would stay at 50 for the next 10 seconds. And then we would go to 100 for the last 10 seconds, right? We would increase another 50. Okay. 101 is kind of an extra problem here, just kind of letting you know what's the average rate of change or the slope between certain points, and this is greater than this. So, sketching the graph of a function with the points A, B, C, and D, right? The average rate of change between A and B is greater than the average rate of change, right? Average rate of change from A to B is greater than the average rate of change from B to C, right? The average rate of change from B to C is less than the average rate of change of C to D. And then the average rate of change of A and B is the same, right? So this needs to be the same as this, C and D. So pretty close there. Okay, and that is lesson 13.3.1.